All right, today we're looking at volumes of revolutions. Now, before we actually get into the flip chart, I want to start with a model to show you what we're talking about. The idea of volume of revolution is that we're taking these areas that we found yesterday and we're revolving them into 3D space to create a 3D shape. This is done with a couple different methods. The one we're going to be using today is a disk and washer method. This top one right here, ignore the bottom one that says shells. The idea is we're creating these small slices of our function and revolving them around some form of axis. When we do that, it creates a disk. Then we're going to take an infinite number of those disks, sum them up to get the volume. So let's actually look at what that looks like here. All right, so here's this function. We'll say the axis of revolution will move up to the x-axis just for right now. All right, we're taking that area right there. We have all these little rectangles that are infinitely small that we're revolving. Now, I'm going to revolve one that's not infinitely small, but this single one will show you what we're looking at. We're revolving this in there, and the idea is to make that rectangle really, really small there. So if we revolve all of them, we see that they're stacking on each other and we're adding them up, and those sum up to the whole volume of that shape. Now, what we really want is to see what this shape actually looks like. So when we take this, there we go. When we take this, we have a single infinitely small disk there that we're summing up throughout that whole area, and we're revolving it into 3D space. And it creates, in this case, this shape right here. So you can see that one disk, there's an infinite number of them, and they're infinitely small, and they give us that shape that we're creating as we revolve into 3D space. Now, the question is, how do we do this mathematically? Well, let's think about the area of one of those disks. We already know what summing something up does. That's an integral. We've seen that before with other integral stuff. So we know we're going to be integrating something. And we'll just say from A to B right now. But we want to sum up an infinite number of those little disks. So area of a disk, pi r squared. Okay, that's the area of any circle. We're going to sum up an infinite number of those. So we'll say pi r squared dr. Now the question is, what is r? Well, r is not just a single distance. If we look back at that model, r is the distance from the function to the axis. So let's define what r is. We'll say r is the radius of that disk. R is the radius of the disk. That sounds like it's what we already said, but that's not always going to be a constant value. So we'll say the integral from a to b of r squared with respect to x. Because our radius is not going to be a set value. It's going to be changing as the function changes. So let's look at our first problem here. It's one we just saw. This one right here, the square root of x from 0 to 4, rotated over the x-axis. And we're going to start with a picture. So here's our y and x-axis. Here's the square root of x. Y equals 0 is this line right here. X equals 4 is this line right here. And we know that when x equals 4, y equals 2. So this is the point 4, comma 2. And then our function. This is the area we're revolving. It says we're rotating over the x-axis. So we're rotating it here. Let's start with trying to set up our radius. So if we had a single disk here, a single disk would go up from the axis to there and then revolving into 3D space. So this is r in this case. This right here is r. Now in our problem, what does r represent? R represents the distance from the function to the axis. So we'll say square root of x, our function, minus our axis, which is 0 in this case. So now we can set up our volume to be pi times the integral from 0 to 4, because that's where we have our intersections at, from 0 to 4. That's our axis there. of r squared, square root of x minus 0 squared dx. Pi integral 0 to 4 of x dx. And then we can solve this without issue. X squared over 2, plug in 4, plug in 0. But this is really just to get the point across. This is what we're doing. Now, it seems very simple here, but it gets more complex once we start changing things. When we start changing what we're looking with respect to. When we start changing where our axis of symmetry is. What if we have multiple functions that we're revolving? All right, so at first glance, this one looks very similar to the one we just did, except this time we're revolving over the y-axis. So let's start by looking at what that does. So we have our function, same exact thing we looked at last time. That's right here, here to here. Have this little area right here. Okay, so this is what we're looking at this time. All right, now when we do this one, we're seeing when we draw our disk and washer, it's revolving around this right here. Now that means our disk should be perpendicular to that line. Now yesterday or in last class, I talked about perpendicular and how it changes things. Well, what this does for us, if we do it perpendicular to the y-axis, that means this problem has to be in terms of y. So if it's perpendicular to the y-axis, it should be in terms of y. So we should have, instead of the function y equals square root of x, we're instead going to use the function x equals y squared. That's the function we're looking at right now. And we're revolving around here. And when we do this, we notice we end up with this gap in our shape. We end up with this hole in the middle. And now we're thinking back to that geometry stuff, that area between curves that we did yesterday. This hole in the middle means we're going to have to take the outer area and subtract the inner area. So we're going to set up our r now as two separate r's. We'll use big R for the outer area. And that outer area is the distance from this line right here to the axis. Well, this line is the line x equals 4, and the axis is on x equals 0, so 4 minus 0, which is 4. And we'll use little r as the inner area. Well, the inner area goes from the function, which was x equals y squared, to the axis, which is 0, y squared minus 0, which is just going to be y squared. So what we end up with, pi, the integral from 0 to, and we're doing it in terms of y, so we need a y value there. That's the y value of 2, 4 comma 2. So 0 to 2 of the outer area, 4 squared, or we'll call this not outer area, outer radius. Inner radius. The outer radius squared minus the inner radius squared. So we end up with pi integral from 0 to 2 of 16 minus y to the 4th dy. And once again, we can solve this by hand if we needed to, but I'm trying to make a video, so we're going to go a little quicker. All right, so this is the outer minus the inner in this case. Okay, now we're going to get a little bit better at this as we do this more, but the idea here is we have to make sure we subtract out that inner. So if we think of this as two volumes, the first one is the volume of the big disk around the whole thing, this disk on the outside. And the second one is the volume of this little inner disk right in here. And we subtract those, and we're left with the volume of this middle disk. Create a little washer there. Okay? Now let's look at some other weird situations. We look at this one. This one, we have two functions now. We have the function x squared and the function square root of x. Those intersect at 1 comma 1 and 0, 0 here, with this one being x squared and this one being square root of x. And we're rotating this one around the x-axis, so around this way. So now, unlike last time, well, similar to last time, we're going to have a hole in our disk. So here's our radius, Here's the outer. And here's the inner. Okay, we're going to have a hole, but instead of one being a constant, we're going to have one that's both of them are going to be changing. So the outer is going to be this outside function, square root of x, minus the axis, which is 0. The inner, let's use this. The inner is going to be this inside function, x squared, minus the axis, which is 0. And so when we set up our integral, pi integral from 0 to 1 of the outer square root of x squared minus the inner x squared squared. So pi integral from 0 to 1 of x minus x to the fourth. Okay? Doesn't change much to what we did last time, but now instead of having one being a constant, they're both functions. And it's a similar concept. The outer is this outside circle here. The inner is this inside circle here. And we're subtracting those two volumes. Okay? Now, this is where things start to get really frustrating for some people. Let's draw it by drawing our area that we're finding. We have x squared. Okay, there's x squared. X equals 0, which is, and I'll do it in a different color. This is x equals 0. Y equals 4. This is y equals 4. That means this intersection is at 2, 4. And then our function x squared. But now it's not rotated around an axis, and around the x and y axis. It's rotated around the line y equals -2. This is what we're rotating around. So the first thing we need to figure out, are our discs going to be perpendicular to the x-axis or the y-axis? Well, they have to be perpendicular to our axis of symmetry. So when we draw it, it looks like it's perpendicular to the x-axis. So wipe the sweat off our brow. We're still working with x's here. We don't have to change anything. But now, when we go to find the outer and inner, it's not revolving around this. It's revolving, we got to revolve this all the way around this axis down here. So this is the center of our revolution. So when we go and set up the outer radius, it's going to be this line right here, the y equals 4. So it's going to be 4 minus, and then our axis of that axis that we're revolving around. Well, the axis we're revolving around is -2. So 4 minus -2, or 6. The inner is going to be the inner radius, which is the function x squared, but also minus our axis. It's the radius is going to be the distance from the function, this here, to the axis we're revolving around, to the center of that circle we're creating. So x squared minus -2, or x squared plus 2. And so when we set up our volume formula, integral from 0 to 2 of 6 squared minus x squared plus 2 squared. And now we're getting into the territory of either a calculator problem or a setup but do not solve problem. Not saying you couldn't solve this, just we're starting to get to where the time is not worth me asking you to solve it. Okay? Let's take this one step further. Now we're going to combine all of these together. We're going to have two functions, and we have a line that is not one of the x or y axis. So let's start by looking at this. And I'm not going to draw it, I'm just going to show you. So these are our two functions. We have the first one in red is y equals x, and the second one in blue is x squared minus 2x. So we see them down here represented. We're revolving around this line right here. So let's think about what our outer and inner R are going to be. And just to give you a reference of what this shape is, I don't know if you can see it, but it's kind of like a funnel that comes down in here. You can see the funnel coming down in there with a bulbous outside to it. Okay, that's what we're looking at here. That's the shape we're creating. All right, so let's think about our radiuses, or radii. All right, so this is the disk we're revolving. This right here. This is the disk. Now, up to this point, the outer has always just been the one on top. But when we look at it here, the one that is outside is not the one on top. It's the one furthest from the axis we're revolving around. In that case, that is the blue one. So our outer is going to be, or is going to involve the blue one. Now the other issue here is that we can't do the function minus the axis. I mean, technically we could, but mathematically it's not the best way to do it. The best way is to pick the bigger thing when we're subtracting. Well, what's bigger, the axis or the function? It looks to me like the axis is bigger than the function. So we're going to do 4 minus, and then x squared minus 2x. So our outer is going to be negative x squared plus 2x plus 4. And then our inner is going to be this part right here. Okay, that's now the higher function, but it's going to be the inside of that disk. It's going to represent the inner circle there. And so for the inner, we're going to do the same thing. We're going to take the axis, which is 4, minus the inside function there, which is x, as our inner. And so now we can go to set it up. You have the integral from, and we'll find the intersections in a second, negative x squared plus 2x plus 4 minus, and then 4 minus x dx with our pi on the outside. Don't forget that. And the last thing to do is just find where they intersect. So if we go back here, we see they intersect at 0, and it looks to me like they intersect at 3. I guess we could calculate it if we need to, but I'm going to go off the graph we were given. 0 to 3, and then we just simplify some of this before solving. Negative x squared plus 3x plus 4 minus 4 will cancel, so dx. And there we have it. That's going to be our volume for this one. Oh, whoa, never mind. I forgot to square things. Ooh. Yeah, we're not going to even touch that one with solving. We're going to say that's a calculator or a setup but do not solve. All right, and if you want to see where or some of the reference to this. Oh, I don't have the other picture on there. Okay, well, I'll just show it to you another day. All right, so that's the idea behind these. It's a lot going on. Mathematically, it's going to be the same thing. We're always doing an outer radius, an inner radius, and the radius is found by doing whatever you're revolving around and whatever the outside part is. Conceptually, though, it becomes a little tough because you got to be able to draw it and be able to visualize what is my outside, what is my inside. So make sure you're asking questions and let me know if you have anything that you need help with. You'll have a great day.